4B. So we're going to get into actual chemical equations now. And what chemical equations are, basically when you are a chemist and you mix stuff in a flask. Okay, the stuff that you're putting in the flask is called the reactants, and then the stuff you get out after the reaction happens is called the products. So we can represent it as a chemical equation by having the reactants on the left side of the arrow and the products always on the right side of the arrow. So you can almost think of this arrow as an equal sign. I add this reactant to this reactant and it equals these products. So how we're going to use this is there are 5 different types of reactions you need to know for the course, and I have all 5 written here. They're also on the PowerPoints as well. And in this chapter, it starts talking about synthesis and combination first. So what you're going to need to be able to do with these types is if you are given a chemical equation, you need to be able to identify it as one of these 5. So I'm going to go over how to do that. So for synthesis combination reactions, on the reactant side, so the left side of the arrow, we usually have 2 compounds or elements separated by a plus sign, and they are combining together to form one product. So an easy way to identify this one is 2 or more reactants equaling one product. And I'm going to do some examples over here. We're going to label them, we're going to balance them, we're going to do all sorts of stuff with them. But I wanted to go over the reaction types first. Now decomp, so this is where something's decomposing, it's the opposite of a combination reaction. Because this time I have one reactant. So it's a compound together, A representing one element, B representing another element, so it's a compound. And that compound is decomposing, bonds are being broken, and it's breaking apart into 2 simpler products, or 2 elements. So one reactant, 2 or more products. Next we have single and double replacement. Now sometimes these are called single displacement and double displacement. They mean the same thing. In your book and in your homework, they call it single replacement. So that's what I'm going to try to use. I might inadvertently say displacement once in a while, but I'll try not to. So for single replacement, notice we have a compound, A and B together, 2 elements combined as a compound, reacting with an element by itself. So this C, it's an element all by itself. Okay, it could be oxygen, it could be copper, it could be a multitude of things. And what's happening is this compound is going to kick, this element, excuse me, is going to kick B out of that compound so that it can pair up with A. So what you can see on the product side is now A is with C. So C, the element that was by itself on the reactant side, is no longer by itself. But since it kicked B out of its spot, now B is by itself. So to recognize this one, you're going to have a compound with an element by itself on both the product and reactant side. It's just the element by itself is going to be different on both sides. Double replacement. Notice now there are no elements by themselves at all. We got 2 compounds together. Right? We have an AB compound and a CD compound. And what they're doing is they're switching partners. So A doesn't want to be with B anymore. So A goes and partners up with D, and that leaves B and C together on the product side. And once we start looking at these reactions, actually with single and double replacement and combustion, we're going to be predicting the products for them as well. So we're going to be predicting what these products are on the other side of the arrow. We probably won't get to that today, probably on Wednesday, but we will be able to predict the products. Combustion is the last one, and the nice thing about combustion, products are always the same. They're always water and carbon dioxide, every time. So that's a good way to recognize that one. For the reactants are always some sort of hydrocarbon, and we talked about hydrocarbons in the last chapter. That's where we have just carbon and hydrogen in the element. So some sort of hydrocarbon reacting with oxygen, oxygen being the fuel source, providing the combustion reaction to happen. All right, so what we're going to do now is I'm going to put up some examples. We are going to identify the type of reaction given the chemical equation I put up, and then we're also going to balance, because I haven't talked about balancing yet. And balancing is really just trial and error. The more you practice, the better you're going to get. There's not too many tricks to it. There's a few that I'll try to point out here and there, but all right, what do I got? Let's do this one first. I have this one in my Gen Chem class. I'm going to put spaces. Okay, so the reason I'm putting spaces in front of each element or compound is because when we balance it, we're going to be putting numbers in those spaces. So that's just to remind me what I can change, where I can put numbers. But before we talk about balancing, what type of reaction is this? So look over here and see, well, I have two reactants combining to make one product. So I said the name of it and just describing what's happening. So synthesis or combination, right? It's going to be two elements or compounds combining to form one. And that's exactly what's happening there. So now to balance. Why do we balance? Because what we need is conservation of matter, conservation of energy. That's a rule that applies. Like you always need to have the same amount of things on both sides. Nothing can be created or destroyed here. They're just being rearranged. So what that means is, on this side, the reactant side of the equation, I need the same copper and oxygen atoms, the same number as I have on the product side. Okay, so how do I achieve that? By adding coefficients in front of the elements and compounds. So I can put numbers here. What I can't do is add subscripts. Okay, because if I decide to add a subscript, I just change that compound. It's no longer the same compound. And that's not allowed. I can add more of that compound, so I can add 2 of them or 3 of them, but I can't change the structure of it. And that's what changing a subscript does. So how I like to approach this is just make a list of the elements. And we're starting off with kind of easy ones. We'll look at some harder ones. And then writing how many do I already have. And to figure out how many you already have, you take the coefficient and multiply it by the subscript. And right now there is no coefficient, right? We don't have any numbers here. So we assume it's just a 1. So looking at copper, we're just looking at the subscript to tell how many coppers there are. So how many coppers on the reactant side? Just 1. And then for oxygen, its subscript is 2, so 2 oxygens. Now I do the same thing on the product side. And here, I don't have any subscripts after copper or oxygen, so it's just 1 of each. And from there, I look and see if it's balanced. So I look and see if it has the same amount on each side. Now the coppers are matching up, right? I have 1 copper here on the reactant, 1 on the product. My oxygens are not. So I have 2 oxygens on the reactant side. That means I need 2 on the product side. So I have to put a number here to make this 2. So what number would make it 2 oxygens?
2.
A 2, right. So what that does is I do coefficient times subscript, so 2 times 1 gives me 2 oxygens. But notice, putting a 2 here changes every element in that compound. So copper's changing as well. How many coppers do I have? 2 as well. So I've balanced my oxygens, but now my coppers aren't balanced anymore. So I go back to the reactant side, go to where copper is, and now I need a coefficient to put here to make 2 coppers. Putting a 2 there does it. So this would be the balanced chemical equation. A 2, and then there's a 1 here. You usually don't have to put a 1. It's just assumed. But 2 to 1 to 2. I never did write the type, did I? Synthesis. So we're going to identify what type, and then we'll go ahead and balance. So we have magnesium reacting with hydrochloric acid to make magnesium chloride and H2.
They kick out, so that would be
It is the single, yes. And while we're looking at this one, let me talk about something else quickly. Type is single replacement. Oftentimes, with a chemical reaction equation, what you're going to see, and I'll write it in a different color to kind of make it stand out, is little letters in parentheses after each element or compound. Just let me point out what those mean quickly. If you see an S after an element or compound, these are the states of the matter, what state that is in. So S means it's just a solid. So that means this particular reaction, they took a solid piece of magnesium. And I wanted to do it with this one because it has almost every one I need. If you see an AQ, so AQ means aqueous. And what aqueous means, probably spelling that wrong, is that it's dissolved in water. So it means HCl, this isn't straight hydrochloric acid. This is diluted hydrochloric acid. It's hydrochloric acid with water in it, and it's soluble. They're soluble in one another. They're dissolved uniform throughout. Okay, and looking over here at the magnesium chloride. Magnesium chloride is an ionic compound. That means it's most likely a solid at room temperature. But the AQ tells me that they dissolved that solid in water. So it's a solution form in this reaction equation. The last one we have G, that just means it's a gas. So if you were actually going to do this reaction, and it's actually pretty cool, you have a solid piece of magnesium, you add the hydrochloric acid, and you're immediately going to start seeing bubbles. Because those bubbles are that hydrogen gas escaping. The only other one that I don't have on here is an L. You'll see that once in a while. It's very rare just because this means the liquid in the pure form. Usually water is the only one you'll see an L by. Everything else will most likely be aqueous if it's in a liquid form. So with that, let's go back to balancing. So making a list, I got magnesium, I got hydrogen, and I got chlorine. I'm going to do the same thing over here, and I like to put them in the same order so that I can compare them better. So that's why I have magnesium, then hydrogen instead of magnesium, then chlorine. As long as they're all there, it doesn't matter what order you have them in. So first thing to do is go through and see how many you have starting with. Then you go back and change the coefficients to balance. So magnesium, there's just one. Hydrogen, just one. Chlorine, just one. That side was easy. Okay. Magnesium over here, just one. Hydrogen, two. Remember, hydrogen's one of those diatomics in nature that we talked about when there were 7 on the periodic table. That's why it's H2. It's not just hydrogen by itself. Random aside. How many chlorines? 2 as well. Okay. So my magnesiums are balanced, so I'm going to leave those alone for now. So I'm just going to go to my next one down. Hydrogen, I only have 1 on the reactant. I have 2 on the product. So I go to where hydrogen is on the reactant side. I need it to have 2. So what coefficient goes there? 2. So that changes my hydrogens to 2, but notice chlorine's a part of that compound. So how many chlorines do I have now? 2, and that's good because that's exactly what I needed. Now my chlorines are balanced too. So this is the balanced chemical reaction. 1 to 2 to 1 to 1. The nice thing about single replacement and double replacement reactions is they're usually fairly easy to balance. It's the combustion reactions that are hard. I have trouble with those. I'm going back and forth like 10 times to get those balanced. All right, let's try another one. So when you get to the homework and you start balancing these or writing some of them, sometimes they'll ask you to put the states of the matter. And when they're asking that, they're asking for this solid, aqueous, gas thing. But sometimes they say don't put states of matter. So just be aware of that in the homework. Sometimes they ask for it, sometimes they don't. So, oh, we just did a hydrate lab, so let's try this one. most likely be water vapor as a gas. Okay. So what type of reaction is this? And this is what we did with the hydrate lab. We took a hydrate and we superheated it until we got all the water molecules off as a water vapor. So we have copper 2 sulfate pentahydrate on the reactant side. On the product side, we have copper sulfate by itself and then the water molecules by themselves. So we've separated them. So going down the list, synthesis, it would not be synthesis because you would have 2 reactants, 1 product. We're not seeing that. We have 1 reactant and 2 products. So my next choice down to decomp. 1 reactant breaking apart to form 2 products. Yeah, I'd say that's it. This is 1 compound. This is 1 by itself. Because these water molecules are trapped inside that crystal structure. So this is 1 compound by itself, and what we're doing is we're breaking it apart to drive off the water molecules. So it is decomp. It's kind of a hard one to see. Because those hydrate compounds, we're just not used to seeing them. It's a little weird to have that multiplication times water molecule thing. So a decomposition reaction, let's go ahead and balance it. This one should be pretty simple. But I want to show you with a trick with balancing. So when you have a polyatomic, so this SO4 is a polyatomic, keep it together if it stays the same on both sides. So notice SO4 and it stays SO4 on the product side. So if I keep it together, it's going to make my life easier because then I'm not counting the sulfur separately and the oxygen separately, so on and so forth. It's the same with this water molecule. Do I want to split up the hydrogen and water or oxygen? Not if it's exactly the same on this side. It stayed together, so when I'm counting, I can keep it together. So copper, sulfate, and water. Let me grab a different color. All right, so let's start with the reactant side. How many coppers? 1. Now, since we kept the sulfate together, SO4, we're looking at how many SO4s? 1. It's just 1, right? And the waters, how many of those?
5.
It's the 5 because of this coefficient here. This is a little different than we're used to. There's a coefficient in front of just the water portion. So there is 5 water molecules on the reactant side. So when we go over to the product side, we got 1 copper, 1 sulfate. How many waters? 1. So that water is the only thing not matching up. So I go over to the waters on the product side, and what number do I want there? 5. Done. I'm doing different ones than I had on the previous video. Trying to. All right, so type of reaction, let's start there. So going down a single replacement, we have a compound reacting with an element by itself.
Is the next one double replacement?
Next one, right. So when you have 2 compounds switching partners, then it's double. Double replacement. And one thing I want to point out with double replacement is these are often precipitation reactions. Not always, but most of the time. And what precipitation reaction means is it forms a solid as one of the products. And that's what we use our solubility tables that I posted on Blackboard for, is to figure out which one of the products would form a solid. So before we do that, let's go do our balancing. Get that out of the way before we introduce something new. So the nice thing about double replacement reactions is when they have a polyatomic, a lot of times the polyatomic stays. So that means when I'm making my list, of course I have PB, lead, but this NO3 I can keep together, just like I did in the previous one, because it stayed together on the product side. It's still NO3. I also have sodium, and then CO3 is also a polyatomic. And I'm going to write the same over here. I write it in the same order, but it's your choice of personal preference. And CO3 just helps me compare it better. So once I have my list, I start seeing how many of each I have. So how many leads? 1. How many NO3s? 2, right. You're looking at the number outside of the parentheses to figure that out for the polyatomic. If there is no parentheses, then you know there's just one of them. So for the sodium, how many? 2. We got a subscript of 2 after the Na. And then CO3 is the polyatomic. So how many of those on the reactant side? 1. Just 1. Yeah, if there's no parentheses, there's just one of them. So lead, we have 1. CO3, I put him over here, just 1. Sodium, just 1. And then NO3, just 1. So kind of all over the place. And what I do is I usually just pick one and start balancing. So my lead is balanced. My NO3s, I'm just kind of going in order here, are not. Right? I have 2 on the reactant. I need 2 on the product side. So I find where my NO3 is, and it's over here. And I need 2 of them, so I put a 2. Right? And that changes my NO3s, but what else does it change?
The sodium.
Changes the sodiums as well. But that's good because that was the next thing I needed to balance. So now it's balanced. So now, since this is a double replacement, let's look and see if it's also a precipitation. They're not always precipitation reactions, but they oftentimes are. So how we do that is we're looking at just the products. Okay, we're not looking at the reactants. Because it being a precipitation reaction means that a solid is formed, so that means it would be one of the products. So to do that, you look at the ions. So we have CO3, -2, and a +2. And it doesn't matter right now how I got those charges. But to tell you, NO3, I would look at my polyatomic table. It would say it's a -1. For sodium, since it's an alkali metal in group 1, I know it's a +1. CO3, same thing. I would look this up in the polyatomic table, and it would tell me it's a -2. So I would know that lead has to be a +2 to cancel out that negative. Because there's one of each, so they cancel. But the reason I'm pointing out the ions is because you'll notice if you look at this solubility table, it's full of ions. So I'm looking at the ions and seeing what matches. So we have, in the top table, it says soluble. So what that means is all of these ions on the soluble side can be soluble. Doesn't mean they always are, it means they can be. When they're not soluble, so when they form a solid, it's when they're with an exception. So for instance, let's look at sodium Na+, that's in the soluble column, right? So it's saying that it can be soluble. Then when I look at the exceptions, my exceptions are none. So what that means is sodium ion, no matter what it's attached to, is always going to be soluble all the time, no exceptions. So sodium ion will never form a solid when it's in an ionic compound. So this is not the precipitate, this is not the solid. Soluble means dissolved, okay? So what this would be an AQ. Remember, that's that aqueous. It's dissolved in water. So now if I look at the lead carbonate, so just look in your list and see if you can find either of those ions. I see the carbonate way down here in the bottom table. So now the bottom table, notice it says insoluble for those ions. So what that means is that most of the time when you have one of those ions, CO3 being one of them, they do form solids. Then the exceptions would be they're soluble when they're attached to these guys. So that means CO3 will form a solid unless it's attached to lithium, sodium, potassium, rubidium, cesium, or the ammonium ion. Is it attached to any of those?
No.
No, so that means CO3 will form a solid in this case, because it's insoluble unless it's attached to one of those. So this is my solid, S. And you could actually go through and see, using the solubility tables, that these two reactants are actually both aqueous. So fun, let's just do that. For my kind of fun anyway. So NO3, that's that ion, right? NO3, right here, same guy. They switched partners, right? So NO3 is in the second row. So it says it's soluble, meaning does not form a solid, and it has no exceptions. So that means no matter what NO3 is attached to, it's going to be aqueous. It's going to be soluble. It's going to dissolve. So this would be AQ. Now, looking at this one, you can use either ion. Okay, you could look for the sodium ion and see what, like we did over here, we said sodium, no matter what it's attached to, is soluble. There's no exceptions for it. So that means it will be aqueous. But you could also look up the CO3 part, because CO3 was in this insoluble section, but its exception is sodium. And that's what it's attached to. So that means, no, it's not insoluble anymore, because sodium is its exception. So that's how we use those tables. And we'll use them a lot more and get more practice with them. This was just the introduction to it. So I want to try a harder one to balance, because I feel like the ones we've been balancing haven't been too intense. But we're also going to name the type, because why not? All right. And I haven't balanced this one yet, so bear with me. Might take a while. So what type of reaction is this?
Well, that's the combustion. It's the carbon and hydrogen.
Right, so at first you want to say it's a combustion, which it could be, but it's missing the oxygen, the fuel. So we'd have to say plus O2 here. In order to get the water, it needs to be water and CO2. So water and CO2 are always going to be the products, and then you need the oxygen, pure oxygen on the reactant side. But this is one that could be combusted. It's just we're not adding oxygen, so that's why that's not happening in this case. So let's see, synthesis, two reactants, no. Decomp, one reactant, yes, but is it breaking apart? Into two? It is breaking apart. Because here you have 6 carbons, right? So they broke apart. Yeah, so it would be decomp. One reactant, 2 products. Okay, so now this one's going to be really hard to balance. Let's give it a try. And the reason it's hard to balance is because if you look at the product side, oxygen's in 2 different places, so we have to keep track of a lot of moving parts here. So I'm going to write my list: carbon, hydrogen, oxygen. Right over here as well. And then start by writing how many of each I have. And remember, we're looking at the subscripts to tell how many. So how many carbons? Okay, hydrogen, oxygen. Right, now on the product side, well, we have carbon in 2 spots too. 2 here, and then 1 here. So we're going to have 3 right now.
Hydrogen is 6.
Hydrogen's just in 1 spot, so it's 6.
And then oxygen is
3 as well. I'm gonna put 1 plus 2 equals 3, so that I can keep track of it as I go. If I change the number here, I know I change this guy. Change the number there, I know I change that guy. Just gonna help me keep track of it a little bit better. So, it's all over the place. Pick one and just start going. And it's gonna take a lot of back and forth. What I would choose personally is I would try the hydrogens first, because that's the only thing that's only in one spot. So it's gonna be less confusing for me. So I have 12 hydrogens on the reactant side. I want 12 on the product side. So to figure it out, you're saying, what number can I multiply 6 by to get 12? 2. Because 2 times 6 would give me 12. Because you always do coefficient times subscript. So if I put a 2 here, I have 12 hydrogens. But it's going to change all the elements in that compound. So it's changing my carbons too. How many carbons do I have now? 2 times 2 would be 4. And I'm just changing this carbon. So my total has changed to 5 now. And then oxygens, I'm changing this first oxygen. How many oxygens have I changed? I have 2 now here. So it's going to be 4. All right. Now just pick another one and go from there. Let's see, over here, I have 4 oxygens and I only have 6, right? I guess we could do carbons too, it really doesn't matter. But if I wanted 6 over here, what number, let's change this oxygen, what number could I put there? 2, because 2 times 2 is 4, and I'm just changing this one, so that would be a total of 6. But I changed my carbons as well, right? 2 times 1 is 2.
And then now it's balanced.
That was balanced already? I thought that was going to be a harder one. I mean, it still was confusing because you're keeping track of 2 spots, but I thought it was going to take more. So that's balanced. 1 to 2 to 2. Wow. This next one's going to be harder, I swear. Because I don't want to do that. Sorry. 6, 8, 14. 2. Okay. So first, let's look at the type of reaction. So we're looking at all these types, going through the list and seeing, is it synthesis, is it decomp? Now it's what?
Now it's
Combustion. So combustion is a hydrocarbon, so carbon and hydrogen. It can have oxygen in it sometimes too, but you're reacting it with pure oxygen, that's the fuel, to get water and carbon dioxide. Yes. And it's combustion, yes. And it doesn't matter which way this is. So what I mean by that, it doesn't matter if I have the water first and then the carbon dioxide over here. It's interchangeable. So this would be combustion. Let me erase this so we don't think it's double replacement. Now this one I think is going to be harder to balance. So let's make the list. We have carbon, hydrogen, and oxygen. Carbon, hydrogen, oxygen, both sides. We're looking at the subscripts to see how many we have right now, because we're trying to get the same amount on both sides. So how many carbons on the reactant side? 6 hydrogens, 14 oxygens, 2. Carbon is just in one spot on this side, so that's nice at least. There's just 1. Hydrogens, 2 because of the water. Now oxygen's in 2 places, so we got to be aware of that. So 3 total. So, what do you want to do first? Carbons or hydrogens? I'd save oxygen since they're in multiple places. Carbon? Okay, so we have 6 on the reactant side. We need 6 on the product side. So here's where carbon is. So what number do I need here? 6. Because there's a subscript of 1. So if I put a 6 here, 6 times 1 gives me 6 carbons. But it's also going to change my oxygens. To figure out how many oxygens, I take the coefficient of 6, multiply it by the subscript on oxygen. There's 12 oxygens now. So instead of the 2 that I had here, it's 12. Now I have a total of 13. So my carbons are balanced. Let's just move down the line. Let's do hydrogen next. I got 14. I need 14. Notice I have a subscript of 2. So what times 2 is going to give me 14? 7. So if I put a 7 here, 7 times 2, I now have 14. So they're the same. My oxygen is going to change too. So 7 times, and there's a coefficient of 1 after the oxygen. So 7 times 1 is changing the second one here from a 1 to a 7. Oh, I knew this was going to be a hard one. Okay. Some of these get up into like double digits, and it might be one of those. I haven't done this one yet, so we're experiencing this together. I need 19 over here. Is there any way I'm going to get 19 over here? No, there's not. There's no way. So what you have to do at that point, because this is always going to be even number, right, is there's a 1 here right now, okay? What I would do is start by changing it to a 2 and just seeing what happens, because you only want to go 1 level up. I don't want to all of a sudden change this to a 4 or a 5, okay? But I know that this is going to have to be more than 1 because I'm going to have to be changing all of these other things. So if I change it to a 2, let's see what happens and then keep going from there. So how many carbons do I have now?
12.
How many hydrogens? All right. So let's go back to carbons again. So what number do I need instead of the 6 here?
12, 6. No.
So there's a 1 after carbon.
Oh.
So and I need 12 of them. Yep, so it's going to be 12. So that changes this to 12, but it's changing my oxygens to
24.
12 times 2 is 24. So I'm still at an odd number. 31. Wait, that's 31, right? Yeah, okay. But I gotta change this guy too. So I've done carbons. My oxygens are still crazy. Let's see if this will help. So I need 28 hydrogens. What times 2 gives me 28?
14.
14, yeah. So 14 times 2 would be 28. Okay. But I also changed my oxygens, correct? How many oxygens are here in this water right now? 14. 14 times 1 tells me there's 14. Now I have an even number, so now it might work. 38? Okay. So carbons are good, hydrogens are good, oxygens are even. So what number do I need here that I can multiply by 2 that gets me 38? I honestly have no idea.
17.
Is it 17?
Yes.
17.
19.
Is it 19? Oh, 17 would be 34, wouldn't it? This was as good as mine, I have no idea. So now it's balanced, okay, like big numbers. But the key here is when you're looking at it, you want to make sure that you can't lower it any further. So what I mean by that is we have an odd number and we can't reduce this any further, so that's good. If you had all even numbers, that means you went too far up and you need to reduce it down. That's why I started by just putting a 2 here instead of a 3 or a 4. Just start with your lowest numbers and work your way up. So these will be the hardest type, in my opinion, to balance, because you have the oxygen in multiple places and they get to kind of be really big numbers. Running out of time, am I? Okay. We have time for another one. Maybe even 2 more. So, and what we're going to do on Wednesday is we're going to continue this exact same thing. It's just we're going to start predicting the products instead of me giving them to you, because that's part of what we're going to be learning as well. But for now, I want to focus on types and balancing. I know I have more than that. boring one to balance. But we can do the reaction type at least. So remember, these little letters after are representing the states. S for solid, AQ for aqueous, meaning it's a solution, it's dissolved. So we would use these types of reactions and try to place it with one of these patterns. So notice we have iron, it's an element by itself. We're reacting it with copper 2 sulfate, a compound. It's going to be single replacement, right? We have AB would be, where's my colors? This guy here. And this would be C, right? So we're switching. So single replacement reaction. And the reason I said this isn't a fun one to balance, it's already balanced. I have one of everything. I got one iron, I got one copper, I got one sulfate, one iron, one sulfate, one copper. And a lot of times with single replacement reactions, sometimes they are just balanced on their own. Same with double. I think I ran out of examples. No, I didn't. I have one more. Good. Because I don't want to get into predicting products and then leave you confused at the end. Since we only have time to do just one. But there it is. Yeah. So this is sodium hydroxide and hydrochloric acid. So this is actually an acid-base reaction, but since we haven't talked about acid-base reactions, we're going to classify it as one of these types. We'll actually talk about acid bases, I think, in chapter 8 or 9, quite a ways away. But it does fit into one of those categories as well. Let me write this CL a little bit better so it looks like it's separate. So just go through the list. Do I have 2 combining to form 1? No.
No.
So I have 2 products. Do I have 1 breaking apart to form 2?
No.
No. Do I have a compound with an element by itself? Do I have any elements by itself?
No.
No, they're all compounds. So my next choice is compound, reacting with a compound, switching partners.
Yes.
Double.
So it's going to be a double replacement reaction, right? All right, so let's balance it. I don't think this one is not balanced yet, so we can actually do that. And I said before, if you have a polyatomic, as long as it stays the same, you can keep it together. So this is OH, this is a hydroxide ion, but notice it's not staying together on the product side. So what I mean by that is we need to separate this into oxygen and hydrogen separately. Not keep it together. We also have hydrogen in 2 spots. Look at that. Make it a little bit more interesting. So I'm going to do that over here too. Sodium, my oxygen, my hydrogen, my chlorine. I just keep it in the same order. All right. Let's see what we have to work with starting. So we have how many sodiums?
1.
Dang it, I think it is already balanced. How many oxygens? 1. How many hydrogens total?
2.
Oh.
Because we have 1 here, and then the 1 there. So I think it's already balanced. Then chlorine, 1. All right. 1 sodium, oxygen, just 1. 2 hydrogens, because of that 2, it's only in 1 spot, and then 1 chlorine. So that one is balanced too. But it didn't look like it right away when I just glanced at it. Sorry, like I said, single and double replacement, they're boring to balance because they kind of balance themselves. It's the combustion and the synthesis and the decomp ones that are kind of fun. So, you guys want to do 1-1? Fun. I think this one might be under lab. I don't know if I did it in the video or not, but it's okay, I'm going to balance. All right, so let's start by type.
There's combined, so synthesis.
It's combining. We have A being